Good evening, everybody. Rod Hine. I'm glad to see that he's here tonight and everything electronic-wise, I'm hoping, is working well. So, born just after the war, he was about 10 when his Aunt Florrie gave him a book for Christmas. It was The Boy's Book of Space by Patrick Moore. He was already interested in anything to do with science and engineering, and he devoured the book from cover to cover. Shortly afterwards, Sputnik 1 was launched, and seeing it pass over London clinched my interest in physics and space travel. Pretty soon, he was deeply involved in electronics and amateur radio. He passed the RAE in 1962 and later took up the call sign of Golf 8 Alpha Quebec Hotel. He took physics, chemistry and maths at A-level, and in 1964 went up to Churchill College, Cambridge to study natural sciences. He later switched to electrical sciences and after graduating joined Marconi at Chelmsford, working for several years on satellite communications. That job eventually took him to Nairobi, Kenya, after which he worked there in the meteorological communications and later switched to teaching at the Kenya Polytechnic. In 1972, he married a Yorkshire lass he met in Nairobi and finally moved back to the UK in 1976. Since then, he's had a variety of jobs in electronics and industrial controls and was a co-founder of Bradford Instruments Limited, which designed and supplied industrial control systems from 1982 and only finished trading in 2012. From about 2000, he's been lecturing part-time at the University of Bradford, although now seems to have been retired as the electrical engineering department has been wound right down. He got back into astronomy about 1992 when Josie bought him an astronomy book and he joined Bradford Astronomical Society. He's currently chairman of Bradford Astronomical Society, and mostly because no one else is prepared to do the job. Very simple, very similar to a lot of societies. Anyway, can you all put your hands up and welcome Rod Hine.
Thank you. Perhaps I'd just better correct the record. That's slightly out of date because I finally did manage to divest myself of the chairmanship of the Astronomy Society at Bradford, and that's now in the very capable hands of Sue Stubbs, who's doing a great job. But anyway, we'll get these notes up to date one day. Right, I shall just share my screen and then we can begin. So just bear with me.
Okay, that's
now if I'm lucky, that should just say lucky breaks in astronomy.
Yes, it does.
Right. Okay. So let's get started. The idea for this talk came to me some years ago, and I realised that there were lots of cases where people set out to find something and then they find something completely different, or alternatively, they set out to find something and miss the thing completely. So the idea of lucky breaks came in, and so we'll start off by just thinking of this word of rather nice word, serendipity. If I can make the screen change. Just a minute. Yeah, so this word serendipity comes from a fairy story about the three princes of the Serendip in Sri Lanka. That was a fairy tale that went back, and it's come to mean the faculty or phenomenon of finding valuable or agreeable things not sought for. So we'll start off with two things that were found quite by accident. So we start with the story of Telstar. As I've said, this has sort of vague links to my past history, which is what led me to these different trains of thought. So let's just see if this will play. I think I'm just going to have to carry on because that's so apologies for that not working. Right. Okay. So I'll go back. Have you now got the picture with Telstar still?
We have.
Right. Okay. I'll just have to skip the sound effects, unfortunately. Okay. So So some of you may remember the rather cheesy pop song that was current in 1962 when the first Telstar satellite was launched. And remember, it was quite an achievement in those days to send colour TV signals across the Atlantic. The development of Telstar started around 1960 as communication satellites. And originally they were just completely passive. But then eventually the Telstar satellite was put up in 1962. And that was in a low Earth orbit. And that meant that it was only in the sky for a few minutes at a time. But nevertheless, it enabled transmission of television signals from the UK, from the United States to Goonhilly Downs. There was also another French station at Plumeur-Baudou in Normandy that was also receiving at the same time. And the original station was built at Andover, Maine. There was also a relay station at Homedell, New Jersey. And all these stations were originally built for the ECHO satellite project, which was the totally passive one. But the point we're coming to is that by 1962, there was this transatlantic link using the satellites and those antennas. Let's just get that right. So I'll do that. Yeah. So there's your picture of the different sites. Goonhilly Downs over there. If I just use where's the pointer gone? Spotlights. So the original satellite dish at Goonhilly Downs was built for that, and the one at Plumeur-Baudou in France was a big antenna inside a radome. It's quite impressive. I'll show you the thing inside. And across in the States, there was another antenna inside a radome at Andover, which was the transmitting site. And there was also a monitoring station at Homedell, New Jersey, using this rather curious antenna, which will figure later in the story. So what happens next, if I can get the right one? So inside the radome at Plumeur-Baudou, there was another one of these strange antennas. They're called a hoghorn antenna, and as you can see from the bottom two, they're the Homedell and Plumeur-Baudou. They consist of a great big horn-shaped device that swings round on a turntable and has an aperture that faces up to the sky. So some of you may remember that on the very first night of the transmission across the Atlantic, the signal was terribly bad. You may remember Raymond Baxter doing his best to put a brave face on this, and while a very flickering picture rolled up and down across the monitor screens and on the TV screens, he was saying, "Yes, I can see a picture. This is exciting. This is the first transmission across the Atlantic ever." And meanwhile, round the back, as I discovered later in my career, round the back, all of the post office engineers, you can see one of whom's hand is reaching up to a monitor, and the bald-headed guy was a Scotsman called Jock, you can see just at the top right of that picture. They were all having kittens because the signal level was 40 decibels down on what it should have been. That's to say it was only 1/10,000th of the power that they'd expected to receive. And they quickly established that the French station at Plumeur-Baudou was getting a perfect picture. Well, it turned out that this was good old British arrogance. The British engineers hadn't checked the convention for left and right-handed polarization of the signal. And the Americans followed the IEEE convention, and they viewed the source from the source in the direction of propagation. But a lot of textbooks used the other way. The French had the foresight to actually check with the States what was actually going on. But the British engineers in the post office just thought they knew it all. So a friend of mine later, a later guy I met later, as it were, he and another guy had to go up in the pouring rain overnight and take various bits of the feed apart from a Siemens platform in the pouring rain and change the polarization around so that the next night the pictures were perfect. So that was a little bit of a side issue there. But the answer was that once the basic principle of the satellite had been established, the Homedell antenna wasn't needed anymore, so that was taken out of service. And the next year, in 1963, Robert Wilson and Arno Penzias were given instructions to refurbish the Homedell antenna for radio astronomy. The idea was that in future development of the satellite systems, it would be useful to be able to calibrate dishes by doing a little bit of radio astronomy. And it turns out that the signals from the Cassiopeia supernova remnant are very strong indeed, just in the right range of frequencies that the satellites needed to use. So the idea was to set up a receiving system to calibrate the Homedell antenna so that it could be used as a standard to compare the radio transmissions from other satellite dishes when they were put up. So they set about it, these two guys, given a little project to do, and their first job was to obviously refurbish everything. And what they were trying to do was to measure what's called the G/T, the gain to noise temperature ratio. The important thing is to make sure with the receiving antenna that it's got sufficient gain. In other words, does it pick up enough signal? And secondly, does the receiving system and all the rest of the system have a sufficiently low noise to allow the signals through? There's no point having a high gain signal if it's swamped with noise. So one of the first things they had to do, having got started, was to measure the amount of noise in the system. So what did they find? Well, they connected up to their antenna, and they would switch the signals between the antenna itself and a dummy load and a receiver cooled to 4.2 Kelvin with liquid helium. That would give them a reference temperature of 4.2 Kelvin of noise to compare things to. So they made their measurements and they found they had about 100 times too much noise, far too much to be put down to just casual experimental error. And the first assumption was some problem with the antenna, or alternatively, something untoward they hadn't thought of. So what did they have to try to eliminate? Well, they said, was it stray noise from New York City? Because Homedell's only about 30 miles away from New York City. And it's a well-known fact that large city conurbations generate a lot of thermal noise and radio noise. They said, was it that? They fairly quickly eliminated that as a source. They considered, could it be fallout from the 1962 nuclear tests? Those of you who perhaps remember those nervous days when we used to hear about the Russians and the American testing ever bigger nuclear bombs and hydrogen bombs. And eventually they couldn't find any other causes. They wondered if it was a result of the pigeon droppings in the antenna, because the antenna had been disused for a while and had been taken over by a pair of pigeons that had covered the whole of the inside of the horn liberally with what they called a white dielectric material. In other words, pigeon poo. So they spent a long time cleaning every tiny scrap of it out until the whole thing was spotless. And eventually they were driven to the conclusion that the noise was actually coming from the sky. Now, at this stage, they were quite new to any sort of astronomy kind of things because they were radio technicians, but they realized that they had to try and eliminate it. So they observed this noise signal from different times of day with different positions from the antenna. And eventually they concluded that it was indeed completely uniform microwave radiation from every part of the sky. It didn't matter what time of day it was, what the conditions. As far as they were concerned, they could measure this constant noise from everywhere. So that became quite an interesting thing, and they were persuaded to write it up as a paper and publish it, just as good researchers do. This was sort of just one step in a whole series of amazing coincidences, because only 30 miles away, an astronomer called Robert Dicke was working on theories about the Big Bang. Now, of course, we all know about the Big Bang. It was the derogatory name that Fred Hoyle coined. Fred Hoyle, our local hero in Bingley. And it was Gamow and Lemaitre's cosmology theory suggested that there should be some kind of low-level radiation left over, which they called the embers of creation after the Big Bang. And these altogether, three guys got together, Dicke, Peebles and Wilkinson, and they began to wonder if they would actually be able to see this radiation. And remember, they knew nothing about Penzias and Wilson's work going on at the same time. Jim Peebles actually wrote a paper on this, predicting the results, and he predicted that it would have a noise temperature, a temperature, as it were, of 10 Kelvin. And that was one of the excerpts of the graph that Peebles produced in 1965, purely theoretically. And basically, that they would work on the principle if they could get anywhere within an order of magnitude of that, then they would consider that a good first step. So that was the theoretical work that was going on just at the same time. So Peebles wrote this paper, but there was a little bit of problem over rights to this, because, as you all probably know, the world of academic publishing is a mass of people fighting over who had the priority, who thought of the first idea, and who should be quoted and what credit should be given to previous work. And it turned out that this was a bit of an overlap on some work by Gamow Alpha and Herman and a few others. And so Peebles was persuaded that it wouldn't be right to actually publish the paper as it stood until they'd sorted out those wrangles. So again, this good idea remained completely quiet and nobody thought of anything of it. But Peebles did present his ideas to a private group at Johns Hopkins University in early 1965. This was just a discussion group, not an official release of any information. It just happened that there was a chap called Kenneth Turner from Carnegie, Washington, in the audience. And he told the story later to a friend of his, a chap called Bernard Burke. And it just happened that Burke was a friend of Arno Penzias. And Arno Penzias had discussed his discovery with Bernard Burke about this noise that they'd discovered in this antenna. So eventually the penny dropped and they realized that they needed to get together. So eventually the theoretical guys with Dickey and Peebles and all his group, they got together with Penzias and Wilson, and they decided that this indeed was the explanation for the cosmic background radiation. So it was discovered totally by accident. Now, it's very, very generously, the theoretical people shared the credits with Penzias and Wilson. So actually, in the end, there wasn't too much acrimony about the publication eventually. And the ironic thing was that Wilson had been trained in the Steady State School of Astronomy. And of course, he was deeply troubled because he had inadvertently discovered one of the cornerstones of the Big Bang theory, which troubled him as a sort of philosophical point at the time. But eventually they all got together and they jointly submitted a paper about this in the Astrophysical Journal in 1965. And they gave the equivalent temperature as 3.5 Kelvin, which is not too far away from Jim Peebles' prediction of 10 Kelvin. Even more strangely, some years before that, in 1960, a chap called George Field had been working on observations of cyanogen gas in interstellar space. And he too, using some receiving equipment, had problems with his receiving system. And he had reported an all-pervasive noise at 3 Kelvin to describe the discrepancies. Now, even more strangely, his office was opposite the building occupied by Dickey's group. And on top of the building, this chap saw this strange contraption being assembled, which was it. Oh, excuse me. Just mute the phone. Yeah, he saw this strange object being built just opposite, on the top of the building opposite. I wondered what the heck it was. Of course, not realizing that it's actually a piece of equipment that was being hastily put together to try and confirm these results. And he moved on to Berkeley without even being aware that that was what was going on. So there's all sorts of amazing coincidences and missed things. In fact, that strange structure was a radiometer being built by Dickey's group to try and repeat the measurements to confirm the discovery of Penzias and Wilson. This chap called Dickey had been working on the radio, had invented a radiometer whilst working on radar during World War II, which was where quite a lot of these guys actually learnt their electronics and microwave engineering from. So that was the story of the background of the discovery of the cosmic microwave background radiation. Roland Wilkinson, they completed their radiometer a bit later, and they came up with a value of 3.5 Kelvin. And again, they all came together and they published the results in late 1966. So there's quite a number of people converged on this, but by and large, it was Penzias and Wilkinson who got most of the credit. And of course, we know that subsequently quite a lot of interesting satellites have been put up to make the better measurements. The first one that was really successful was the Kobe satellite in 1989-90, and that made a series of measurements which fitted perfectly on the spectrum shown there on the graph at 2.735 Kelvin. I would point out that that's a bit of a misprint, really, that it shouldn't really say degrees Kelvin. It should say Kelvin if you're being really strict about it. But it was probably an American publication, so we'll let them off. So, Nobel Prize comes into this story, and Penzias and Wilson duly received the Nobel Prize in 1978. And of course, we all know as good astronomers that the cosmic microwave background radiation forms a cornerstone of much of the present day cosmology. And in fact, it's by studying the finer details and the fine-grained structure of the cosmic microwave background radiation that quite a lot of the models of the modern models of the universe are actually based on that. So that's one little story, discovered completely by accident. Part 2, Little Green Men. Well, just as that chap Dickey had worked on radar in the USA and returned to academic life, there was a certain Anthony Hewish who had worked on wartime radar in UK and returned to Cambridge in 1946 to study radio astronomy. He had been broken off from his original studies to work on radar. He returned to Cambridge in 1946 and graduated in 1948 and immediately set about doing research in the fledgling science of radio astronomy under such people as Martin Ryle and a few others at Cambridge. Now, the young Tony Hewish was quite an expert on radio and making measurements, and he came up with some really good ideas around 1965. He wanted to study the scintillations of faint radio sources, because it was realized that as more and more radio sources were being discovered and catalogued, it was realized that some of these sources seemed to scintillate or flicker if you made measurements of their signal. And that flickering was attributed to variations in the density of the electron clouds in the atmosphere and, of course, also in interstellar space. So the idea was that, excuse me. The idea was to study the scintillations or fluctuations of the signals from radio sources with a view to two points of view. First of all, studying the scintillations would reveal something about the variations of electron density in interstellar space and the clouds of gases that wafted along between the source and the Earth. And secondly, he also realized that if you could understand the way that scintillations were produced, you would also be able to make a very quick estimate of the angular size of a radio source. This is a rather interesting idea, because quasars had just been discovered a few years before that, and more quasars have been catalogued. And these were found to be extremely small angular size radio sources. Now, it turned out, of course, that if you have a really practically a point source, then you get more intense scintillation. This is very much akin to the fact that if we look at stars, particularly say if you look at the star Sirius, when it's low down on the horizon, you can see that the light from it scintillates quite dramatically. That's because of the variations in the atmosphere of the Earth. Same thing goes for radio waves. If you have a point source, then it will scintillate more. On the other hand, we know that if you look at planets such as Jupiter, then even right down on the horizon, that hardly scintillates at all, mostly because it is a much larger source a larger angular size, and therefore not susceptible. So there were two things he wanted to do: A, study the actual structure of the interstellar environment, but also to very quickly be able to identify radio sources like quasars, which had a very small angular diameter, angular size. Basically, he needed an antenna that was very, very sensitive to pick up faint signals, and that had a very fast response so that he could measure the rapid variations of the signal levels. So he set about designing that. It turned out that eventually, in its final form, he had 1,024 individual antennas, dipole antennas. That's an array of 32 by 32. And altogether, that was made up of 120 miles of wire strung up on 4,000 poles right across a big field just near to Cambridge. So it covered several acres in the end, and it produced a very, very narrow beam of reception from the sky, and it was scanned purely by the Earth's movement. It wasn't steerable at all. And it was connected to a sensitive and very fast-acting receiver, that's to say with a wide bandwidth. So that was what they were setting out. And eventually, this piece of kit came on stream in about 1967, and the measurements were begun. So within a few weeks of the instrument going online in 1967, his chief assistant, Jocelyn Bell, started to examine the chart recordings. There were no computer data collection in those days, so it was all done on chart recordings, and Jocelyn Bell and various other of his assistants had to search through these paper chart recordings every day to see what had actually gone on. And purely by chance, she noticed what she called the bit of scruff that kept reappearing at the same time each day at a wavelength of 3.7 meters or 81 megahertz. Well, say same time of day. The interesting thing was, of course, that it repeated on the sidereal time. In other words, the sidereal day, 23 hours, 56 minutes. So clearly it had to be effectively some kind of stellar source. So that was what piqued her interest. And she and Hewish decided to focus a bit of attention on that. They improved the resolution of the receiver system, increased its bandwidth, and they stepped up the speed of the chart recorder whenever this particular new source came into view. And it turned out that if they speeded up the chart recorder, they could see that this signal that looked like a bit of scruff, a bit of noise, actually was a repetitive train of pulses, exactly every 1.33 seconds. In fact, it wasn't long before they could measure it to 1.3373011 seconds, which was basically more accurate than your typical quartz watch. Now, this back in 1967 was the total jaw-dropping stuff. And Hewish and Bell were very worried about this. They christened it LGM1, Little Green Men 1, and they wondered could it be from an intelligent being. And again, just as Penzias and Wilson had tried to eliminate all sorts of possible sources of error, they had to look at all sorts of possible sources that might be causing interference. But they couldn't pin anything down that would repeat on the level of the sidereal rate. So it clearly was from outside the Earth. It clearly was locked onto the stars, and it clearly was a genuine signal. And they were really worried about this because they thought they were going to cause a lot of problems if they mentioned it to anyone. Fortunately for them, quite soon they discovered another one, and then another one after that. So by the time they got 3 or 4 of these objects with different pulse rates and from different parts of the sky, they rather sort of they produced a bit more confidence, and they decided that it was safe to publish. And in publishing, Hewish suggested that these were either spinning neutron stars or spinning white dwarf stars. Now, it just turned out that the theory of the spinning neutron star had been proposed in the 1930s by Oppenheimer and Franz Zwicky. So once the two things were put together, it was widely accepted that these repetitive signals were actually from neutron stars that were spinning. They were christened pulsars. Here's a picture I'm sure you've seen, the idea of the the spinning neutron star that spins on its axis and beams radiation around. And if that beam of radiation happens to sweep across the Earth, then any instrument listening to that will pick it up. If you see from that chart on the right-hand side, the pulses are not all entirely regular. And that's just because of the variations in the path, in the propagation. But the period is pretty well accurate over a long period of time. Each individual pulse may vary very slightly. So that particular side panel shows 400 consecutive pulses, and you see they are altogether pretty well in line, those little peaks on the graph. So fairly easy to identify once you know what you're looking for, and it wasn't long before plenty of these were discovered. Now here, I'm afraid I don't think I can play you any sounds because I actually have all the sound files for these, but it didn't seem to work. I'll just give one a try, but if it doesn't work, then we'll just have to give up. Nope, not working. Okay, so basically the sort of pulsars that Bell and Hewish found to begin with, they were mostly in the order of 1 or 1.5 second, 1.5 or 1.5 hertz. That's the pulses per second. So for instance, the first one there just goes tick, 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 tick. Then there's one in the velar pulsar, which in the velar cloud, which has a frequency of 11 hertz. And that comes out as sort of a whirring noise. And in fact, later pictures, actually, if you take a gamma ray picture, the Fermi Space Telescope was actually able to pick up the variations in the gamma rays. So there you can actually see the slowed down version of the velar pulsar, normally going at 11 pulses a second, slowed down in the gamma ray. And in fact, there are other pulsars. In the middle of the Crab Nebula, there's a pulsar that goes at 30 hertz, which is a buzzing noise. And there's a little story about that, because many years ago, sometime in the 60s, in the United States, one of the universities that had a public outreach scheme for introducing the public to astronomy, they had an open night, and there was some research assistant who was showing off his big telescope, and some woman looked through and she said, "Oh, that's interesting," and the man said, "Yes, that's the Crab Nebula you're looking at," and this woman just from the public said, "No, that's interesting. I can see a little flickering light in the middle of it, just a flickering star going, looks like a flickering star." And typical bloke, he said, "Oh, no, madam, you're imagining that. No, there's nothing like that there." But it turned out there is actually an optical pulsar at 30 hertz, 30 flashes a second, smack in the middle of the Crab pulsar, in the Crab Nebula, and that is the Crab pulsar. And that's one of the few pulsars that actually has visible flashing light as well as the radio signal. And then the remaining two files were 174 hertz and 642 hertz, which is quite a screaming noise. But sadly, we can't play those for technical reasons. I shall have to look into that. So there we are. So that was some of the work on pulsars, again, discovered completely by accident. In 1974, Hewish got the Nobel Prize along with Martin Ryle. Martin Ryle was mentioned for his work on interferometry, which Ryle and Hewish had worked together on the early days of the interferometry system, which they used at Cambridge, and Hewish was mentioned for the pulsars. Rather controversially, Jocelyn Bell wasn't mentioned at all, but she was quite gracious on this, because she said in a later interview that it wasn't the done thing for research assistants to be given the Nobel Prize, although some people, particularly Fred Hoyle, was quite offended, and they said that she should definitely have had the Nobel Prize for it. Chatting to Hewish, and I have to introduce a personal note here. At this time, I was an undergraduate at Churchill, and Tony Hewish was my director of studies. So there were many times that he used to, once we'd done the supervisions and got over the hard work of these things over a cup of coffee or a glass of sherry after a supervision, he would talk about his work, and we got the story of all this firsthand as things were going along. And later at a reunion, I was talking to Tony Hewish, and he was quite unabashed because it was basically his design of the telescope that made the discovery possible. It was just, it could have been anybody who had the job of looking at the results they should have found it. So anyway, you can discuss that if you like. I know other people feel very strongly that Bell should have had the Nobel Prize. Of course, Jocelyn Bell went on to do fantastic stuff in the field of astronomy education, and has well deserved her damehood for it. But that's one of those little things in history. Should she have had the Nobel Prize? Well, maybe yes, maybe no. Just as a little personal obituary as well, Tony Hewish only died a few weeks ago at the ripe old age of 97. And as I said, it was a great guy to talk to. And it must have been about 15 years ago was the last time I spoke to him at a college reunion. He was a very, very, very cheerful, avuncular guy, and actually a very devout Christian, as it happens. So it's quite an interesting chap to talk to. So those are two things of discoveries. Now, what about missed opportunities? Well, of course, one of the biggest foul-ups in the discoveries in astronomy must be the story of Uranus and Neptune. We probably all remember that Uranus was discovered by William Herschel in 1781. And of course, like any new planet's discovery, it was avidly tracked by a lot of observers. And it wasn't long before people realized that Uranus wasn't playing by the rules, as it were. Because people realized when they made observations after a few years that Uranus didn't seem to be moving at quite the speed that they had anticipated. At first, they attributed the discrepancy to the presence of Jupiter or Saturn, but the numbers just didn't quite work out. And it turned out that the discrepancy that caused Uranus to speed up and slow down, it had to be a planet with a bigger orbit than Uranus, because the orbit of Uranus speeded up from 1781 to 1822 and then began to lag behind towards in the 1840s. Now, over that period of time, both Jupiter and Saturn would have moved quite significantly, so clearly they weren't the cause of the perturbation. There's a little diagram showing the relative positions and the fact that there seemed to be something pulling on it. And so eventually the idea came about that there must be a planet outside the orbit of Uranus that was exerting an influence. And it was just a case of calculating and making the best measurements to try and locate where that particular planet was. There was a chap called John Couch Adams from Cornwall, newly graduated at Cambridge. He started to work on the problem in 1841. He made quite a lot of progress, and he tried to interest a chap called Airy, then the Astronomer Royal. But Airy was very, very sceptical about the whole thing and didn't like the idea of devoting time to ideas promoted by just a lowly fresh graduate, and didn't offer Adams any support at all. Adams eventually sent his predictions to a chap called James Chalice at Cambridge in 1845, September, hoping to get some observations done with the telescopes that were available at the Astronomy Centre in Cambridge. They had some quite decent telescopes by then. As it happened, somebody else was working on the same idea, a chap called Liberia, and he had spent several years working on the orbit of Mercury, which showed the same sort of discrepancies. But then in 1845, he decided to look at the problem of Uranus, and he worked out the likely orbit of the new planet from the measurements. And in September 1846, he wrote to his friend Johann Galley in Berlin. Now, contrast this with poor old Couch Adams, who had no luck persuading anyone to take any interest. Johann Galley was immediately fired up by the idea. And so Chalice, I've jumped a slide there. Chalice had lots of other tasks and was put off the work because the star charts that Adams had used were not up to date. So he had to do all sorts of other measurements before he could check on Adams's observations. But back in Berlin, Galley received the letter on the 21st of September 1846, he began the search. And within hours, using Leverrier's predicted position, he found the new planet. And of course, there was no prize for being second in this. And it wasn't until several weeks later that Chalice actually found Neptune and was able to confirm it. It was a bit of a row about that because Adams and Leverrier had actually made the predictions almost simultaneously and equally accurately. And Airy and Chalice were made to look very foolish. And there was a lot of controversy and a lot of arguments and backbiting. But eventually it was agreed that the credit could be shared between Adams and Leverrier. So it worked out not too bad in the end. But spurred on by success, Leverrier decided to push his luck, and he went back to the calculations of the story to the problem of Mercury. And having had success with co-discovering Neptune, he dug himself a really big hole and hypothesized that a new planet called Vulcan had to be really close to the sun to explain the perturbation of Mercury's orbit. And of course, people looked for that, but nothing came of it. And it wasn't until 1915 that Albert Einstein was actually able to explain the effect of Mercury's orbit irregularities because of general relativity effects with the proximity to the sun. So Leverrier actually pushed his luck and didn't come out of that well at all on the second attempt. But he and Leverrier and Adams shared the credit for discovery of Neptune. Now, it just turned out when people began to look back through the records, even when Uranus was discovered, it was actually found that Uranus had been observed at least 12 times between 1690 and 1781. But it had always been recorded as a star because nobody had quite followed it up on it. And also Neptune had also been recorded in 1795 and 1845, just before the official discovery, again, recorded as a star. But that's not the half of it. Something even more astonishing. Galileo himself had observed Neptune several times in December 1612 and January 1613 without realizing it. And if by the benefits of the internet, you can go back and you can download extracts from Galileo's notebooks. So here we have on the left-hand side, now you might not be able to see the top of, can you see the top of this? I've got a bar across on the top of the screen and I can't see this, but it says base.
I can see the date 1612.
Oh, right. Okay. So you can see it. I can't because there's a bar across and I can't seem to move it. Yeah, so it says 1612 and the XMBR, that's December, day 27, and it's got the hour record, ora, so this is all Latin, remember? And so that's the date and time. And you can see from that little picture there that he's observing Jupiter and he's observing the moons of Jupiter moving backwards and forwards along that line. And as a reference point, he's using a star there, which he calls FXA. Okay, can you see that? That's just up on the left-hand side. So he's made his measurements here, and then he shows it a bit later. He shows the orbits having moved around. There's Jupiter, and there are the moons moving on their plane. He's made a bit of a mess of that, so he's crossed it out. And then 1613, again, he's doing the same measurements, and this time FXA is over that side. Okay. Now, it just turns out that so-called star that Galileo thought was a star actually turned out to be Neptune. Now, what a coincidence. There is Galileo leading one of the first serious observational astronomers. He just chances upon the discovery of the moons of Jupiter. While he's doing that, Neptune happens to come into view. And even more amazingly, if you play this through on a planetarium program, and this, I'm afraid I'm unable to repeat this because I can't load SkyMap Pro onto my new laptop, but this is a screenshot from before. So here we have Jupiter, and there are the green dots are the moons of Jupiter. And over there is a little tiny white dot, which is actually Neptune. And if you run the time forwards an hour at a time, what you find is that corresponds exactly to Galileo's star FXA that he used as a reference point. And not only that, it actually gets occulted by Jupiter. There's a close-up of it. So on the 3rd of January, 1613, if Galileo had actually been making an observation at exactly the correct time, he would have seen Neptune go clean behind Jupiter and come out the other side. And if that isn't a bit of serendipity, I don't know what is. So I think that brings my little presentation to a halt, and apologies for not being able to recreate that live for you, which I normally try to do, but this new computer setup completely defeated me. So hope we haven't done too badly, and apologies for missing out on the sound effects. And I hope you found that interesting. Thank you very much.
Thank you very much, Rod. That was really interesting. And I'm sure we've got some questions for you. So can you stop sharing your screen, please?
Yep. Okay. Just let me find it. There we go. Hang on.
Right.
Yeah. Let me just move. Yeah. Just move my screen. That's it. Okay. Yep.
So we've come to Rod. Once again, thank you very much. Serendipity. I think you have to work at serendipity. You just can't stumble into it all the time. There was a lot of hard work going off in the background there.
It certainly was, yes. And in fact, there was another rather serendipitous thing that I've tried to research. There was one of the astronomers I met later from Cambridge called Roderick Willstrop. He had made some observations with a rather strange telescope that he designed, the 3-mirror telescope at Cambridge. It was quite a little project on its own sometime in the 60s and 70s. And he had actually discovered something, or rather failed to discover something. And it was all there in observations that he had made when whoever it was else claimed the credit for something. He went back over his notebooks and found the exact phenomenon in his notebooks, all recorded, but not properly followed up. So there are lots of these things that have worked both ways, either discoveries or missed discoveries. So it's quite an interesting little sideline, this.
It is. Right, ladies and gentlemen, I'm looking for questions, and I'd prefer a digital hand if you can manage that. Otherwise, wave at me. Catherine, unmute yourself, please.
Right. Do you think there's some serendipity in the way that mathematics and mathematical physics and theoretical physics actually track each other with things like curved space, and non-Euclidean geometry and things like that?
Well, yes. I mean, who was it who said that? Was it Einstein that said maths was unreasonably successful at predicting things? I forget. Can anyone help me on that quote? Who was it? Somebody made a comment.
The effectiveness of mathematics.
That's right. The unreasonable effectiveness. Yes, that's something that's always occurred to me. Even just in engineering, sometimes it's really lovely when all the maths and the sums actually work out and something just drops out nicely, and you think, wow. Yeah. I think as those of us who are lucky enough to work in science and engineering, I think we have a lot more fun than a lot of these other people. I don't know about you, but
yes. That was said by Eugene Wigner in 1960.
Oh, right. Okay.
Yes,
yeah. Very good.
Yes.
Well, I'm afraid I'm not a good enough mathematician to actually comment on that. I studied that sort of stuff at Cambridge, obviously, and I wasn't doing too badly. I could follow the maths until we got to the subject called tensors.
Oh yes.
Now, if you have to really understand general relativity, you really need to a dab hand at manipulating tensors.
Yeah.
And I found that with tensors, I attended the lectures on the subject, and I could follow what the lecturer was doing. But when I went back to my digs and tried to work out a problem, I hadn't the foggiest clue how to actually start. But if somebody showed me how to do it, I could do it. I don't know if that makes sense to you. So I very quickly realized that was going to be in my nemesis. So that's why after 2 years of studying natural sciences, I changed to electrical sciences, otherwise known as electrical engineering.
Yeah.
And that fitted in much better, because most of the time, unless you're dealing with elasticity and things, most of the time in engineering, you can get by with vectors. You don't necessarily need tensors. So I found that was just about right, and my maths was able to handle it. So then I went on to do telecoms professionally.
Yeah.
So again, never needed to manipulate tensors again, but I became quite reasonable at differential equations and that sort of stuff for Fourier transforms.
Well, actually, tensors came from mechanical engineering.
Well, they do. I mean, they're very useful. Again,
tensor is French for tension, and if you actually work out a stress tensor and things, that's where everything came from.
Yes. Well, I mean, again, I could just about understand the stress tensor, but when it became really abstract and you have to try and get your head around curved space and time, and that was a step too far for me, I'm afraid.
Okay,
thank you very much.
Thank you.
Okay.
Mick Nichols. Mick, can you unmute yourself? Thank you.
You mentioned about the pulsar in the Crab Nebula that was seen visually by that lady. Does that mean that there's two pulsars in Crab Nebula then? One that can be seen visually and one that can't?
No, it's one and the same. It's whether you can see it or not is just a physiological quirk, because most people can't see 30 hertz flashing. For most people, that's beyond the what do you call it? The persistence of vision. So most people looking at the Crab pulsar, they may see the little star in the middle of it, but it'll just look like a constant light. But a very small number of people can actually see flickers at 30 hertz and higher. And I'm told that people like that can quite easily visually see the crab, the little star flashing in the middle of the Crab Nebula. So that's quite. There's only about, I think there's only about a dozen really well-known pulsars that have a visual equivalent to the radar. So quite a few have gamma ray flashes in time with the pulses. Well, not in time, because if they're far away, the signals get dispersed. But you know what I mean. If you're into that kind of thing, you'll understand it. The signals at vastly different frequencies and wavelengths, they can actually be slowed down very slightly, because what we talk about as free space isn't totally free. There's just enough electrons and things knocking around to cause dispersion in some parts of the universe. So the gases and the electrons that are floating around, it does actually cause dispersion. So, for instance, if you get a lot of fast radio bursts, now this is interesting. Fast radio bursts, if they're seen at really high frequencies, short wavelengths, they seem to come more or less instantaneously. But it's been recently discovered that some of the fast radio bursts, they are observed in the hundreds or thousands of megahertz range. There is a signal that comes down in the 100 megahertz range that can arrive 3 days later. So that's something that's been only appreciated recently, and that's due to dispersion. It's the same event happened, but the lower frequencies and longer wavelengths, they get retarded they get dispersed by the intervening space over hundreds or millions of light years. So by the time the signals arrive at the Earth, they can actually be separated in time by up to several days.
Thank you.
Right, thank you, Michael. Ian Hargreaves, Mid-Kent.
Yeah, hi, thanks. Just a quick question, Rod, and it follows on from Mick's question about the Crab Nebula pulsar. That was the one, wasn't it, that Hewish and Bell discovered?
No.
Oh, wasn't it?
No. The one they discovered had a frequency of 1.33, the original one. They never discovered any of the faster pulsars.
Oh, right. Okay. Thanks for that.
All the ones they discovered originally were in the region of 1 to 1.5, 2 hertz.
Oh, right. Okay.
I'm not quite sure why. It was probably just, don't forget, it was probably a quirk of their particular instrument. They were observing with a very specific instrument at a very specific frequency of 81.5 megahertz. That frequency was chosen so as to be below the broadcast band and above the then common VHF TV band. So
yeah, and of course to fit the dimensions of the aerials
and the dimension. Yes. So they designed it for that on the grounds that was in that sort of region of wavelength. That was about the best they could do in terms of not being troubled by man-made interference, at least. So.
All right. Okay, thank you for clearing that one up for me.
Yeah, no, the Crab pulsar was the Crab pulsar was discovered quite a bit later, actually.
Thank you.
Thank you, Ian. Jez Robinson.
Evening. Yeah, I just wondered where you thought the next advancements in radio would be.
That's a
because I was recently reading about them using radio for trying to discover dark matter. They've found a way of cooling the radio waves down significantly, and they're trying to detect dark matter. But it seems like there's a lot of noise going to be out there, and it's going to be hard to decipher between that and everything else. But I just wondered what your thoughts are on advancements of the radio technologies.
Right. Well, So there's. In terms of radio astronomy, then there seems to be there are two main areas where developments are being made. First of all, there is a move to what I call the multi-pixel radio telescope system. Now, if you think about it, the original radio telescopes, as used by Lovell and Hewish and all these people, basically each dish is a single pixel. It just measures a signal level from a particular spot in the sky. You can measure it over a wide spectrum of different frequencies, but spatially it's just one lump, one bit in the sky. Now, in Australia, they've produced a whole array called ASCAP, where they have 60 odd quite sizable dishes. I think they're 12-meter dishes, and each of those is fitted with a kind of a multi-pixel sensor, so that each of those dishes generates an array of 6x6 beams, so 36 beams. So you have there the ability to construct a map of the sky very, very quickly, because you've got 60 antennas, each of which has 36 individual beams pointing at different spots in the sky. Each of those beams can be analysed over a wide range of frequencies. So this is sort of an area where I think that there's a huge amount of work to be done, and is producing really good results at the moment. And then there's another branch which is looking at rather more esoteric stuff, and that seems to be characterized by effectively sort of almost omnidirectional antennas, but relying on extremely accurate calibration to try to detect variations in the very far red-shifted cosmic microwave background radiation. Because if you think about it, in the early days of the universe, when it was expanding, you all know the story, I'm sure, that up to about sort of, was it 380,000 years after the Big Bang, that's when the temperature fell to about 3,000 Kelvin. And that's when hydrogen atoms began to form, and the universe effectively became transparent. That's when the cosmic microwave background radiation was released at a temperature of 3000 K. Now, if you apply if you allow the universe to evolve, then after a while you get stars, and the stars produce ultraviolet radiation, and the ultraviolet radiation will interact with hydrogen. And so you will get an interaction at 1420 megahertz, the H1 line. So that happened many years ago, billions of years ago. The cosmic microwave background radiation continues to expand And when we now get to the current age, the radiation that we now see in the order of 100 megahertz or so, that is actually the radiation that was interfered and absorbed by the ultraviolet light of the first stars. So there's a number of interesting research projects at the moment trying to look for variations in the cosmic microwave background radiation at these very difficult frequencies to see if they can actually identify the fluctuations in the CMB caused by the ionization of the early stars. And they have found evidence for that. And I think it goes back to something like 200 or 300 million years after the Big Bang. So that's, I mean, that's, you know, that's a Z factor of 18 or so, which is quite astonishing. And that's just being done by really strange antennas in right out in the desert in Australia, miles from any other form of interference, and very carefully monitored and very carefully calibrated to try and pick up these incredibly faint signals at very difficult frequencies. Anyway, so that's my two guesses for progress anyway.
Thank you.
Okay, ladies and gents, I think we've worked Rod hard enough tonight. It just leaves me to ask everybody.
We'll need another cuppa.
To give Rod a big Experience in Astronomical Society. Thank you. Thank you very much, Rod.
Thanks a lot, guys. Good to see you. Be even better to see you in person sometime.